Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology under the LG University. Right now, we have been learning a digital logic design in this particular subject. So far, broadly, we learn about combinational logic and sequential logic. In combinational logic, we learn different modules like full adder, half adder, multiplexer, then BCD adder. In that particular scenario, we didn't apply the clock signal. Again, in a sequential circuit, we learn about the different kinds of flip-flops where we apply the clock signal. So here, we need to define in a way further advanced terminology of defining the sequential circuit as well as a combinational circuit, right? So based on that, we learn something new that we define today here, the synchronous finite state machines, right? Now what are those kind of finite state machine that we are going to learn in both the understanding with the sequential as well as the combinational logic? So further we discuss with what is combinational logic and what is sequential logic. So here the digital logic systems can be classified into combinational and sequential, as combinational circuit can be completely described by the truth table, right? But in a sequential circuit contains the state stored in memory, because in sequential circuit we use a feedback block where some portion of output is connected to back to the input circuit via feedback, and in part of the feedback we take as a memory as a kind of flip-flop, right? So in this particular system, this behavior depends on both on the set of inputs applied and on contents of the internal memory or a state of the system. Thus a sequential system cannot be described with a truth table. Instead, sequential circuit is described a part of the finite state machine or FSM. So let us discuss what is this finite state machine. It's nothing but a finite state machine has a set of states and two functions called the next state and the output function. The set of states corresponding to the possible combination of the internal stages, like if there are n bits of the storage, 2 raised to n possible states, like if 2 raised to 2 there are 4, so we can define a 4 state like 0 0 0 1 1 0 and 1 1, right? Next state function is a combination logic function that, given the inputs and the current state, determines the next state of the system. So further we discuss about this particular model. Let's say generalize, we define the current state as time t stored in the arrays of the flip-flop. Next stage we always define as the t plus 1, and the output time t are nothing but the Boolean function of present state at t time and the inputs at the t time, right? So always we define a kind of present state is a t seconds and the next state is like t plus 1 seconds, right? So the output function here produces a set of outputs from the current state and the inputs. There are two types of finite state machines available. One is a Moore machine where the output only depends on the current state, while in a mini machine the output depends both on a current state as well as the current input. So this is what you can see here. The kind of input is provided to this combinational logic and the output is given, but it's kind of the sequential circuit we define. The next state output is feeding back to the input, right? So this is a kind of storage element where we can define as a memory or you can use as a flip-flop. So obviously this is a kind of the next cycle sequence is again based on the previous cycle sequence, right? So based on that we further define about the implementation of finite state machine. So where you apply the input to the implementation of transition functions where you will get the output, but here the next state output again depends on the previously state input, right? So what we are doing the next state output is feeding back to the memory as a D flip-flop, and again it will come to the input portion, right? So this is what graphically we can represent this particular synchronous sequential circuit analysis with the different types of parameters and the state flow diagram. So we define different kinds of parameters, like what is the state table. So multiple variables tables will be following a 4 sections present state, the values of the state variables for each allowed state input, the input combinations is allowed. Next state is always a t plus 1 state, which is again based on the present state and the input, and the output this value function of the present state and the input. So from the viewpoint of this truth table, our inputs are nothing but the actual input and the present state, and our outputs are nothing but the output and the next state. So from that, if we define one of the example, if we take one of the example based on this analysis of synchronous finite state machine, where our input is x of t, output is y of t, the state is a of t and b of t, where we can define from this particular figure, you can see the input is x of t, the output is y of t, so that's what my y of t. State are like a of t and b of t, so you can define here the output of this d flip flop, this is defined as a of t, the output of this d flip flop, that's a part of b, it's a b of t. And what is the output function? So you can see the output function here, y of t is equal to x bar of t into b of t, because here you can see where one of the function, you can see this is a b of t, and the another one is like, the another one is x bar of t. So here you are going to get it, this one. So once you define this particular AND gate, this particular function is nothing but x bar of t into b of t plus x bar of t into a of t. So that describes your output y. And what is the next state of function? With a of t plus 1 is nothing but it is, see, it's given like that way. So this is what the next state logic is like, a of t into x of t plus b of t into x of t, right? So that shows here the 2 AND gate and 1 OR gate, and b is nothing but only a 1 AND gate. So that's what the next state for this particular stage b, so which is nothing but a bar of t, that a bar we have taken from here, and the another one is x of t. So that's what, how you can define this kind of sequential Boolean functions with the help of this particular digital circuit. So based on that, again, if we want to go for a state diagram or state flow diagram, see, the complete this particular table we represented in form of the state diagram. You can see here the present state is a and b, the input is x, right? The next state of a and b, which is t plus 1 state of a and b, and you represent this the output of y. So again, this output of y is again follow the same equation that we learned in this particular diagram, where you can see y of t is nothing but x bar of t into b of t plus x bar of t into a of t. So based on that, if we learn this particular table, you can see this, the present state is a and b 0 0, the input is x, the next state is 0 0, the output of y. So here, see, that particular state flow diagram signifies something where the this shows the states like 0 0, 0 1, 1 0 and 1 1, right? So based on that one, you can see the present state is 0 and 0, so this is 0 and 0, where input is 0 and output is 0. See, the next state would be the 0 and 0. So again 0 0, this signifies the input and this signifies the output, right? So based on that 0 0, again it will come to the next state as a 0 0 once the input is 0 and output is 0, right? But you can see the next, this is the 0 0, the output is 0 1, but input is 1 and output is 0. So then 0 0, it will go to 0 1, this one, the input is 1 and output is 0, right? Based on that, you can see the third state where 0 and 1, output goes to 0 0. So 0 and 1, 0 and 1, output goes to 0 0, where the input is x, which is the 0, and output is y. And according to that, you can go and you can discuss, or you can see all these 8 states by, we discuss here state number 7, 1 1, that goes to 0 0. So that's 1 1, that goes to 0 0. When input is 0 and output is 1. So input is 0 and here output is 1, right? Same way, 1 1 goes to the next state is 1 0. So 1 1 goes to the next state is 1 0. Input is 1 and output is 0, right? So this is output is 0. So that's how you can draw the state flow diagram, and from state flow diagram you can also draw this kind of table, right? So based on that, we define here, see, this 0 0, this is one of the state where input is 0, output is 0, and the next stage is again 0 0. So As such, there are two variables a and b, so we can break this into a form of four states. So here it can show as part of the input is x is equal to 0. That's why this particular combinations are 8 combinations, so 8 states. We further classified this particular table, or we can reduce this particular table in form of x is equal to 0, x is equal to 1. So in a way, we have reduced this particular truth table into a small truth table where a and b, there are two inputs, so that will show only four combinations, right? So this both truth tables are the same, but this is what the reduced function of, or reduced truth table of the upper one, where you can see the present state, next state and output, where input is 0 1, output is again a kind of when x is equal to 0 and x is equal to 1. So you can see quickly, so present state is 0 0. When it goes to 0 0, where down input is 0, so 1 0 0, it goes to 0 0. When input is 0 and output it's 0, right? The last, you can see the present state is 1 1. The input is x is equal to 0. The output is 0 0, and see, the input is 0. The next state is 0 0 and the output is 1. So this is 1 1, right? It goes to 0 0 when x is equal to 0, right? And when x is equal to 0, the output goes to 1. Same way, it goes to 1 0. So that's what is nothing but the reduction of this particular synchronous sequential logic, where we define the complete uh, synchronous or sequential circuit, where the complete circuit here based on this particular state flow diagram. So this is nothing but a kind of representation of how you can draw the finite state machine using this kind of example. So again, we define in terms of the D flip-flop analysis. You can see this is just the kind of D flip-flop where DA is available with A XOR X XOR Y. So where that particular design, you can see the A here, DA is available with the A. This is the A, so that portion is a A, and X, A XOR X XOR Y, right? So that's what the present state is A, the inputs are X and Y, and next state is A. Again, this particular state, you can see there, if this is 0, when the input is 0 0, say output becomes 0, right? When the present state is 0, the output becomes 1 because the inputs are 0 and 1. So based on that, here you will find a kind of the function is A XOR X XOR Y, and that particular function is given to that particular corresponding bit is given to D, and you will get the corresponding output, right? So that's how you can define a kind of here the feedback portion or output is again coupled with the input, right? So by that way, you can finally see this particular state diagram machine, where you can see the kind of present state is a 0 and the next state is always 1, right? So based on that, X and Y, you can see it 0 goes to 0, so 0 again goes to 0 when inputs are 0 0 as well as 1 1. So you can see this 1 1, right? So state number 0 and state number 3, you can see this 0, the X and Y goes to 1 1, the output goes to 0, right? Once it goes to 0 to 1, see 0 to 1 for this two particular state number 2 and state number 3, you can see 0, where the inputs are 0 1 and 1 0. See your it goes to 1, right? So see this 0 goes to 1 when input is, see, the input is 0 1 and 1 0 both, right? That's how 1 goes to 1 when 0 0 and 1 1. So you can see from this particular truth table you can define or you can draw the state diagram, or from state diagram you can again draw the truth table. So that's, you need to understand how. So based on that particular equation, you can see the final equation of the next state A of t plus 1 is equal to A XOR Y, A XOR X XOR Y, right? Based on that, further we define the kind of, so for the JK flip-flop, there you can see this is a state flow diagram for the JK flip-flop. Now you can define this states are given like SO, S1, S2 and S3, where 0 0, S1 is 0 1, S2 is 1 0 and S3 is 1 1, right? So based on this particular state flow diagram, see this represents the state 0 0, see this represents the input, and corresponding output you can get in this particular truth table. So based on that, you can see the present state, next state, where your input is X. So this 0 that signifies your input. Based on that, you can carry out and you can find your actual input, what should be given at the input, so that you can get your next state based on your present state as well as the input, right? So based on that, we can define this particular digital circuit, where if you see this A and B, where you can see this JA, KA, JB and KB, you can see the JA, this complete state like that way, and that you can also find using the K map as well, right? So this is what, from the state diagram you can go and you can draw the table. From this particular table, if you use the K map, you can again can be able to draw this circuit. So right, there are some important step, like step number 1, the state diagram is given to you. Step number 2, draw the truth table from the state diagram. Then step number 3, go for the Boolean function from the K map. And step number 4, draw a kind of sequential circuit using the J and K flip flop, right? So further more analysis with the T flip flop, where there are two conditions, is like one condition is a no change condition and another condition is a toggle condition, right? So same way in a JK flip flop, we forgot to discuss about the condition. Like there are 4 conditions. One condition is a no change, another condition is a set condition, that reset condition, and last one is the toggle condition. So that you can see the present state is 1 1, the next state is 1 1. So this condition we define as a toggle condition. Right here, this is 1, this is 0, this is 0, and this is 0, right? So based on that, again we go for a T flip flop, and this is a state flow diagram, and from this state flow diagram you can be able to draw a kind of a truth table, and based on truth table, once you follow this, you will be able to draw the digital circuitry, right? So that's how you can represent the state diagram. From state diagram, you can be able to draw the truth table, and from truth table you can be able to design the circuitry, right? So that is what important terminology based on that. So this is how you can represent the sequential circuits. Thank you very much.